So what was that solid? It looked like this. Drawn in the book, the positive x-axis came this way, the positive y-axis went this way, positive z-axis as always went up. The bottom of this solid was an ellipse. X-intercepts of the ellipse were at plus or minus 5. Negative 5 back there. Y-intercepts of the ellipse were plus or minus 3. And the equation of the ellipse itself was z equals f of xy, or not the ellipse, but the solid, the top of the solid, I should say, was f of xy equals 1 minus x squared over 25 minus y squared over 9. When we first started talking about surface integrals, we used it to find surface area. Then we moved on to using it to find mass of a sheet of metal, pretending like the surface here, the boundary surface, was a sheet of metal. And then we talked about integrating vector fields over the surface. And that's where we find the flux. That's what we'll focus on now. But when you find the flux, it's always with respect to a certain direction of a normal vector. If you're finding the flux over a closed solid like this picture that you see, not just one surface, but maybe a couple surfaces pieced together, the convention is you want your normal vectors to be outward pointing. So up here, your outward pointing normal vector might look like this or like this. Down on the bottom of the solid, it'd have to be pointing downward. How can I have a bunch of different ends? Okay, so, the notation gets confusing. It's not just one n. And it's not just a single vector unless it's a very simple situation. In general, with a situation like this, n is a varying vector. It's a function. It's a vector valued function that all happens to be an outward pointing normal vector no matter what point you're at. We can call the upper part of the surface S1, if we like, and the bottom part of the surface S2. The entire surface, in a sense, is the union of S1 and S2. You could write this kind of thing if you like. We're trying to figure out the surface integral of some unspecified vector field. Of course, the problem had a specific vector field relative to the surface, written in the abstract like this. This is the surface here. It's with respect to a surface area element. Say this is an element of surface area, just a plain old S. The fancier S is the surface itself. Surface itself. What does the vector field look like? There's infinitely many choices you could make. Maybe right here it looks like that or something. Over here, maybe it could point into the region. Maybe it points into the region there. You are dotting the vector field with n. Effectively, you're finding the component of the vector field in the direction of n. You could think of this dot product as being the magnitude of f times the magnitude of the normal vector times the cosine of the angle between them. But the normal vector has magnitude 1. So this does simplify to the magnitude of f times the cosine of the angle between them, which is the length of a projection vector along the normal vector. And it's a scalar. It's a scalar quantity. You could think of it if f is representing the velocity vectors of some fluid as having units of, say, meters per second, or centimeters per second, maybe, with fluid. And ds as being an element of surface area, so it's got units of square centimeters. And you could think of this as the little product, if you want, conceptually speaking, centimeters per second times square centimeters, giving you a product that has units of cubic centimeters per second, an amount of volume of fluid passing through the surface, the flux, volume per unit time, for example, cubic centimeters per second. And the integral itself is just like adding those up, so it doesn't change the units. the entire integral is the flux, and it's called a flux integral. And its units are in cubic centimeters per second, for example, as one unit you could use. But the way to compute it is to come up with a parameterization of the surface, or if it's in two pieces like this, two parameterizations for the two different pieces, integrate over each piece and add the results to get the integral over the entire surface. That's the union of the two pieces. You got to use a parameterization, and the way it's typically written is that the flux integral ultimately, through a little bit of work, is a double integral of the param f evaluated at the parameterization, r of uv, dotted with a normal vector that can be found. It's not a unit normal vector, but it's a normal vector. The derivative of r with respect to u cross the derivative of r with respect to v, as long as, assuming this points in the direction of n, assuming this points in the direction of n, same direction as n. dA, it's a double integral, a regular double integral, over some region that you typically hope is a rectangle in a UV plane. You know, it's like you have a UV plane over here, and R is some rectangle over there, and effectively the R of UV maps that rectangle onto some surface in 3 dimensions here. There's your surface. That's a way to imagine what's going on. If this does not point in the same direction as n, then you can negate it to make it point in the same direction as n. Take its negative, which in effect it switches the roles of u and v around. Negative of Ru cross Rv is the same as Rv cross Ru. That's an anti-commutative property of cross products. Effectively, you should have switched the roles of u and v around to be consistent with the direction of n. What's the derivation of that? Effectively, it uses the fact that n is Ru cross Rv divided by its magnitude, as well as the fact that ds is the magnitude of Ru cross Rv dA. Combine those two facts, and it allows you to sort of loosely verify this formula. That's the idea of the surface integral. This is the computational method. As far as our example goes, let's do S2 first. That's the ellipse on the bottom. I'll call it R2 for the parameterization of the ellipse. The bottom ellipse. Effectively, it's like you use polar coordinates. The equation of the ellipse itself in the xy plane is x squared over 25 plus y squared over 9 equals 1. That's the equation of the ellipse itself in the xy plane, ignoring z. And you can use cosines and sines to parameterize not only that boundary ellipse, but also what's inside if you add an extra parameter that is like a radius kind of from polar coordinates. To be consistent with the book, we've typically called the radial coordinate v and the angular coordinate u. It's kind of consistent with the book. And so, for example, you could have picked 5v cos u or 3v sine u using different amplitudes, because x goes between -5 and 5 and y goes between -3 and 3. And then, because it's the bottom boundary, z is 0, we can just take z to be 0. And you could then compute R2u, -5v sine u, 3v cos u, still 0. Maybe I should maybe I should write this as R2 U in parentheses like that. And then R2 V is to differentiate with respect to V. Getting 5 cos U, 3 sine U, 0. And then take their cross product and use your vector field and use the formula up here. Let's go ahead and do that for the vector field from problem 13. It was a simple vector field, just a constant vector field. So R2 of UV 5V times cos U, comma 3V times sine U. It's important to specify, and I haven't done it yet, how U and V vary. When you do it this way, V varies between 0 and 1, and U is like an angular coordinate. It varies between 0 and 2 pi. We also want to parameterize the S1 with an R1. That's the ellipsoid or hyperboloid, as actually it's called. No, sorry, paraboloid on top. Three-dimensional version of a parabola. That was the f function, f of xy was 1 minus x squared over 25 minus y squared over 9. R1 of UV has x and y vary in the same kind of way as our R2 did. It's z that's different. The z is found by plugging those things into f. Like that. It's not too complicated, though it does simplify somewhat. And that's what you could use for the upper ellipse. Now let's go into the vector field. Okay. And do the integral with Mathematica. The vector field for problem 13 again was simple. Just a constant. Constant vector 5, 2, 3. Where is that constant vector in the picture? It would sort of be coming out of the screen towards you. No matter where you are on the surface, whether you're here or whether you're sort of behind on the other side, it's still pointing out of the screen towards you, or whether you're down at the bottom of the surface, it's still pointing out of the screen towards you. It's a constant vector, no matter where you are on the surface. So when I plug in, well, okay, let's compute the cross product as well. Both for R1 and R2. So I'm computing the cross. First for R1 of the derivative of R1 with respect to U. Usually in my answer keys, I think I've been computing that separately. But let's see if it works like this. And the derivative of R1 with respect to V, does that work? Looks like it's working. Sometimes expand is better, sometimes simplify is better. Okay, simplify works better there. So that's going to be R1 sub U cross R1 sub V. We can do the same kind of thing for R2. R2 was for the bottom of the solid. R1 was for the top, right? Yeah, I should have done those the opposite order because that's what we've been thinking about it so far. Let's just copy and paste this up here. What do you do with these things? The integral, the function you integrate is the vector field dotted with these vectors. Use a period for a dot product. Just copy and paste that. Fairly simple function for, that's the bottom. Yeah, that's the bottom of the solid. And then for the top, change the R2 to an R1 and change this too. That's the function we integrate for the top. Well, careful. I made a mistake, didn't I? What do I need to look for? What do I need to change? For the correct function to integrate for the top of the surface. Yeah, put a negative sign in front of this. Why? Because we want an outward pointing normal vector. Negative 15V is not going to be positive. along the top of the surface, we want normal vectors from the picture. I'm just using the picture that have positive z component. My cross product here did not have a positive z component. V varies between 0 and 1, so negative 15v is not positive. It's negative. If you happen to parameterize in some funny way with negative v's, then you'd use that. Is that possible? Parameterize in some funny way with negative v's? It's probably possible. This one was also, no, this one was outward pointing with a negative sign. Negative 15v for the bottom of the surface, your outward pointing normal vector has a negative z component. It points downward. You got to look at the picture. So for the bottom, using this is fine. This is the thing you want to integrate. We are ultimately integrating with respect to u and v over a rectangle. V goes from 0 to 2 pi. No, that's u, excuse me. U goes from 0 to 2 pi. V goes from 0 to 1. Negative 45v. Yeah, v goes from 0 to 1. U goes from 0 to 2 pi. Negative 45 pi. With this constant vector field, the amount of fluid going in has got to be the same as the amount of fluid going out. Effectively, with respect to the downward pointing normal vector, finding a negative flux across S2 means the vector field is going in the opposite direction of n overall. What goes in must come out, at least if it's realistic, and it seems like with a constant vector field, that should be realistic, right? You could definitely have a fluid flow where the velocity vectors are constant. You know, small flow in a small region, effectively the vector field is going to be constant. So the amount of fluid going out should match the amount of fluid going in. So when I integrate that, I should get positive 45 pi so that the net flux out of the solid region is 0. So that's what you should have gotten. I mean, it matched the answer in the back of the book too. Doing that by hand would not be too bad. That's definitely doable by hand here. Positive 45 pi. It's the sum of these two, which gives 0, which is the flux integral over the entire surface. But if I change my example, so this is exercise 13. If I change my example, copy and paste all this, and do a modified exercise 13, where I keep the surface and the solid the same, and the normal vector still being outward pointing, and change my vector field, my f, to being something not constant, and also make sure it has non-zero divergence, div. Remember curl and div? What was div? The divergence of a three-dimensional vector field, f equals components m, n, and q, was the sum of the derivative of the first component with respect to the first variable plus the derivative of the second component with respect to the second variable plus the derivative of the third component with respect to the third variable, written a little bit more quickly with subscript notation. That's the divergence of a three-dimensional vector field. We also did it for two-dimensional vector fields. And you just have two components and two terms there. If I pick a vector field that's got a positive divergence, for example, the integral will not be 0. It'll be positive. So, for example, I could pick f of x, y, z to be, for example, x squared plus 1, comma, x squared times y squared plus 2, comma, x squared times y squared times z squared plus 3. Same surface, same parameterizations. So these cross products are still the same. Those are still the same. But these dot products are different. For R2, which again is the bottom, why is it giving me the exact same thing? That's strange. Oh, you know why? Okay. I think it's because of Z being 0 along the bottom is probably why. And yeah, we're only dealing with the Z component there. And the derivative of this. So what could I do to this to make it different? Let's add an x squared in there. I think it's because I got a z factor of z squared in there that happened. Maybe. Yeah, okay, that's part of it. So that's effectively the value of the vector field dotted with the outward pointing normal vector, unnormalized, because we're using RU cross RV, over the bottom. The integral of that is going to be the flux over the bottom. Our vector field here has all positive quantities in it. It is, generally speaking, upward pointing, but it's not a constant vector field. We should get a negative answer here. Yep. About negative 435.896. For the other one, over the top surface, our vector fields, again, generally pointing upwards and outwards. We should get a positive dot product here and a positive integral. Yikes. Integrate that. Maybe I should expand it instead. Well, I don't know. Okay. We're going to have Mathematica integrate that. We should get a positive answer. I think it's probably doable. I mean, it's just a bunch of powers of v and a bunch of powers of cosine and sine. Theoretically, such an integral is doable by hand, though it'd probably take you 10 hours. But Mathematica can do it right away. Positive number. The final answer for the surface integral over the entire solid is the sum of these two, negative 435.896. Negative 435.896 plus positive 480.075. Positive number, not zero. That's what you should expect when the divergence of the vector field is not zero. Typically, you're going to get something non-zero for a flux integral over a closed surface. Like this gumdrop shape, you could call it. Gumdrop shaped solid, we're doing a flux integral over the boundary surface. The divergence theorem says that you get the same answer if you do a triple integral of the divergence over the three-dimensional solid, not just the boundary. Say that again. So we just did a calculation for this non-trivial vector field whose divergence was not zero. Did a flux integral for it over the entire surface by doing an integral over the bottom plus an integral over the top. The divergence theorem says doing that double integral over such a closed surface like this can also be done as long as the vector field is nice and continuous and has continuous derivatives in the solid by integrating, doing a triple integral of the divergence function over the entire three-dimensional solid. Let's see if it works. What is our vector field? Our vector field is this thing. Let's go ahead and calculate the divergence by hand. Use this formula here. Take the derivative of the first component with respect to the first variable. That's the derivative of this with respect to x. 2x plus the derivative of the second component with respect to the second variable. So differentiate that with respect to y. 2x squared y plus the derivative of the third component with respect to the third variable. 2x squared y squared z. That's the divergence for this example. Go ahead and call it. Well, there is a built-in command called div, but I could call this div f. I may want to plug a three-dimensional point into it, so I'll use curly braces. 2x plus 2x squared times y plus 2x squared times y squared times z. So if I do a triple integral of that function over the entire three-dimensional surface, I should get 44.179. Triple integral over this thing. Let's try it in rectangular coordinates, and let's also try it in maybe cylindrical coordinates and see if we get the same thing, just for extra practice with those things too. Rectangular coordinates, how to do it. So we're back to doing triple integrals, which is actually, in general, you'll see, especially from the reading, it's easier to do the triple integrals than to do a bunch of surface integrals, especially if you had to do it by hand. And especially if you were integrating like over a cube or something. Cube's got 6 sides. You have to think about parameterizations for all 6 sides. Easier to just do a triple integral over the entire cube. I think of the triple integral over the solid, triple integral over the solid D of the function div f with respect to a volume element. I typically think of, and I did emphasize this when we were talking about triple integrals, as a double integral of a single integral. A double integral over the bottom of D. If we think of it as vertically simple, as between the graphs of 2 functions of x and y. For our example, the gumdrop, the bottom function is easy. That's just 0. The top function is the paraboloid. What should I call the ellipse at the bottom? I guess I've already called it S2 for our example. The inner integrals with respect to z, for our example, it's going to have lower limit 0 and upper limit 1 minus x squared over 25 minus y squared over 9. That is also for our example. The divergence function is 2x plus 2x squared y plus 2x squared y squared z. dz for the inner integral, dA for the outer double integral. And then for the outer double integral, I break it into pieces as well. The S2, looked down on from above, is an ellipse, and what's inside the ellipse? This effectively is S2. Again, we're looking down on S2 from above. We're on the z-axis looking down. X can be thought of as going between -5 and 5. What again is the equation of the ellipse itself? It's x squared over 25 plus y squared over 9 equals 1. Solve that for y as a function of x. You get y is, can I do it in my head, plus or minus, well, I'd subtract x squared over 25 from both sides. Then maybe multiply both sides by 9. Then take a square root. Plus or minus square root of 9 minus 9 over 25 x squared. You could factor out the 9 out of that too, but that'll be fine. So x will go from -5 to 5. Y will go from negative square root of 9 minus 9 over 25 x squared to positive square root of 9 minus 9 over 25 x squared. The inner integral is still the same, 0 to 1 minus x squared over 25 minus y squared over 9 of the divergence. I'll just bring it down here. dz, dy, dx would be the ordering. So let's see if it happens. I hope so. -5 to 5. Negative square root of 9 minus 9x squared over 25 to positive. Same square root. Inner integral is from 0 to 1 minus x squared over 25 minus y squared over 9. The function I already named div f. I use curly braces, so do that here. dz, dy, dx, and get a numerical approximation right away. We are hoping for an answer of 44.179. Maybe we have to use n integrate instead. We'll see here. There we go. Okay. So it rounded the other one more. I guess that's because I was using rounded numbers up there. So we're happy. Okay. Could this be done in, say, cylindrical coordinates or spherical coordinates? Would it be, we had to do it by hand? Would it be easier or harder? Let's try cylindrical coordinates. dv is r, dr, dz, d theta. It's going to be easy to describe in cylindrical coordinates. Let's give it a try. See if I can do it in my head. Theta going from 0 to 2 pi. Yeah, it's a little tricky. R does not go from a constant to a constant. It would go from 0 to some function of theta. I'm thinking about the ellipse on the bottom. Maybe this is not so easy in cylindrical coordinates. I'm thinking about this ellipse. As theta goes from 0 to 2 pi, R varies in an oscillatory way from 5 down to 3, back up to 5, back down to 3, back up to 5. I'm thinking about the distance from the origin there. Effectively, the polar coordinate varying as a function of theta. Is that easy to figure out here or not? I mean, I could replace in this equation x with r cos theta and y with r sine theta and see if I could solve for r. That might work. Let's give it a try. I get r squared cos squared theta over 25 plus r squared sine squared theta over 9 equaling 1. Could factor out an r squared. And you could divide both sides by that. I mean, you could get a common denominator of 25 times 9, 225. This could be thought of as 9 cos squared theta plus 25 sine squared theta over 225. Solve for r by multiplying both sides by the reciprocal, solve for r squared. And then solve for r by taking a square root. And we could take the plus square root. But that's kind of complicated. I mean, 225 is a perfect square. It's 15 squared. But I'd still have a square root in the bottom that could not really be simplified because the coefficients of cosine squared and sine squared are different. Let's see if Mathematica can do it. That would be what I'd have to use for my upper limit of the integral here. For r. Yeah. I don't know. I don't know about this. I'm giving it a try, but we'll see what happens. I'm not very optimistic. Z goes from 0 up to the paraboloid again. Have to write that in cylindrical coordinates. And that was this thing. I'd have to replace x with r cos theta and y with r sine theta. I bet doing it symbolically like this, Mathematica is going to spin its wheels. And then for the div function, replace x with r cos theta, y with r sine theta, z with z. Then don't forget to do an extra factor of r as well in there, times r, dz, dr, d theta. Yeah. Give it a few seconds. Then I'll try and integrate it instead. Yeah, let's abort it. Hopefully I didn't make a mistake in all this. as you fixed one of my mistakes already. Let's try and integrate without an integral sign. Z goes from 0 to this. R goes from 0 to this. Theta goes from 0 to 2 pi. Do we get 44.1786? Now a valid limit of integration. It didn't like my limit of integration. For the inner one. Okay. I tried, hoping it would work to do it cylindrical coordinates, but we did do it in rectangular coordinates, and we got the right answer. What we're illustrating here, again, is the divergence theorem. What does it say? I said it verbally, but here it is written out. Let D be a closed domain in space. A solid with a boundary, closing it up, like the gumdrop shape, or maybe like a cylinder or a sphere, whose boundary is orientable, so no Mobius strips to the boundary. Yeah, every example you do is going to be orientable. Gumdrop shape, cylinder, sphere, all orientable. Even a torus of donut shape is orientable. And sometimes you'll see in books them do donut shapes. We're not doing a donut shape because it's hard to parameterize. It is possible, but it's hard. There are other shapes like this one that are bounded by various kinds of surfaces made up of pieces, and you have to integrate over each piece to do the surface integral and add the results. Yeah, piecewise smooth surface, S. Outer unit normal vector. I call that an outward pointing normal vector. So you got your solid, you got to choose the end along the pieces, say, so it's always outward pointing for this theorem to be true. F is a vector field whose components are differentiable on D, the solid domain. So it's continuous and differentiable. Then the flux integral, that's the flux integral of the vector field over the surface that measures the flux out of the surface, out because it's outward pointing normal vectors, can be found by doing a triple integral of the divergence over the entire volume, the entire solid, not just the boundary, but the inside. You're really integrating over the entire three-dimensional solid. Again, part of our goal on Wednesday and early Friday before your review for the final exam is to understand this intuitively. Is that possible? Well, yes and no. Yes, it is possible to understand it intuitively, but no, because it's just still kind of hard to do. It's helped if we try to understand this over small domains, where both the vector field and the divergence are effectively constants. Actually, you think of the vector field as being, I think it's better to think of the vector field as varying a small amount over a small domain, and the divergence is effectively constant. That helps, as is often the case in calculus, if you want to understand things conceptually or intuitively, like slopes of curves. How is it helpful to think small with slopes of curves? Zoom in near any point, the curves looks more and more straight. You can approximate a curve with a tangent. Or if you've got a surface, zoom in near a point and approximate the surface with a tangent plane. Or if you're thinking in terms of integrals, effectively imagine dV to be a small element of volume. And you're multiplying that by the divergence, giving you some quantity that perhaps has a physical interpretation. And the integral is adding those things up, like we did already today when I was talking about it over here. When we were thinking about this flux integral in terms of imagining units. units of flow over small elements of surface area. And the integral is just adding those up. It's not rigorous at all, okay? It's not meant to be rigorous. So don't ever think that when you describe things that way that it's being rigorous. It's meant to be intuitive, but it's a hard kind of intuition. It takes a lot of work and a lot of examples to kind of get it into your soul, you might say. But if you can work to get these ideas into your soul, into your gut, it definitely helps in fluid mechanics and definitely helps in electromagnetic field theory. Fluid flow, the vector field is a velocity vector field of a fluid. Electricity and magnetism, it's either an electric field or a magnetic field.